This year's U.S. Open will be played at the famed Pinehurst No. 2 golf course, the site of the late Payne Stewart's legendary victory in 1999, and his final putt celebration became a statue near the 18th hole. Sadly, he died in a plane crash that October. Payne was a handsome, skilled, and classy golfer with a picturesque swing who won 3 majors and had more coming. He will always be missed by his adoring family, friends, and fans. Welcome back to another episode of Polymer E-Club's Ask Dr. Paul. Today we're going to highlight polymer testing. So when your boss talks about laboratory and analytical characterization of polymers, what do you need to know? For laboratory characterization of rigid polymers, specific gravity helps us calculate how much higher the density in the crystalline sections of a semicrystalline plastics are compared to their amorphous sections. Specific gravity is useful for all polymers, yet I think it is most important for rigid, since fillers such as glass, which increase density and specific part cost, will also increase tooling wear and thus increase tooling costs in high volume manufacturing. Melt flow rate, or MFR, measures polymer melt flow at a known temperature and force, and the units are grams per 10 minutes. MFR is inversely related to molecular weight, so molding grades have lower molecular weight and higher MFRs to fill mold cavities quickly, while extrusion grades have higher molecular weight and lower MFRs, which provides higher melt strength to support the polymer with extrusion, blow molding, and rotational molding. Tensile testing gives us tensile modulus, strength, and elongation, and we know these values are quite different for plastics compared to elastomers. And flexural testing provides flexural modulus by measuring displacement changes with force using a 3-point bend approach. Amorphous plastics generally do better at impact strength compared to crystalline plastics due to their homogeneous structures, and polycarbonate is the leader of the pack at dissipating energy in the polymer and providing high impact strength, maybe 800 joules per meter, from the ability to receive high forces per sample thickness without breaking. Higher molecular weight polymers perform better at heat deflection temperature, or HDT, and that is shown in the table for random copolymer polypropylene. HDT determines the maximum temperature in which a sample deflects with the maximum distance allowed from a known force and rate. In the table, as we decrease MFR and increase molecular weight, while there is no change in polypropylene density and modulus, the HDT increases since the molecular weight inhibits deflection. For laboratory characterization of flexible parts, hardness, either in Shore A or Shore D, is an indentation test in which the values will decrease with plasticizers or increase with fillers, and we know carbon black is a common flexible polymer filler. Having a hardness value in mind is a great starting point for material selection of flexible polymer parts. Tear strength is often important with flexible polymer products like tires, rubber balls, and hockey pucks. Higher tearing comes from an ability to dissipate energy, which increases as you decrease crosslink density. A plot of tearing versus test temperature and test rate for polyisoprene at 2 crosslink levels is shown on your screen, and the lower crosslink 2501 has higher tearing values at normal use temperature, since a looser network has an improved ability to dissipate energy. Compression set resistance, or the ability for a flexible polymer to recover after compression, distinguishes the elastomers from the TPEs, since TPEs have hard or plastic segments, which gives them a more viscous response and inferior compression set resistance values compared to thermoset elastomers. For analytical characterization of all polymers, FTIR is an analytical staple in which the infrared light identifies polymer based on chemical structure specifics. FTIR provides polymer identity, extent of cure, contaminant types, and mixture composition. TGA performs a temperature sweep which quantifies polymer composition. TGA determines volatiles, plasticizer, polymer, filler loading, and thermal stability. DSC performs a temperature sweep which identifies polymer transitions. DSC determines TG, TC, TM, thermal history, and thermal stability. For competitive analysis, we can test an unknown polymer sample and identify it with FTIR, determine if it has plasticizer and or filler with TGA, and determine if it is an amorphous or crystalline polymer with DSC. Knowing 12 common laboratory and analytical characterization tests for polymers? That's working knowledge. Remember to like, subscribe, turn on notification, and even share if you appreciate the content. You can visit our website to learn more about our upcoming polymer testing course. I'm Paul Nash for Polymer E-Club's Ask Dr. Paul. Thanks for watching.